Any sufficiently advanced technology is indistinguishable from magic.
Welcome, everybody, to a very, very special episode of the Into the Impossible podcast. I have had on many professors from Brown University, where I got my PhD. I've had on many professors from the University of Wisconsin-Madison, where I spent some time. And I've had on a few professors from UC San Diego and from Stanford and from Caltech, but I've never had on one from my alma mater, my beloved alma mater, Case Western Reserve University, home of the Fighting Spartans, where I attended from 1989 to 1993. And we're joined by a contemporary of mine and in age, more or less, Professor Stacy McGaugh, who was recommended to me by his, I cannot neglect to mention the mishpacha, the family that put me in touch with you, a legend family. Cal, you're watching. Hopefully, you'll be pleased to see your distant cousin, who's maybe a couple steps closer related to you than I am. Anyway, it's Professor Stacy McGaugh, who's a renowned scientist, cosmologist, astronomer rather, and professor in the Department of Astronomy at Case Western. His fields of expertise include studying low surface brightness galaxies, galaxy formation, and their evolution, as well as testing dark matter and alternative hypotheses. And he is perhaps not the least of which he is known for making novel predictions about the cosmic microwave backgrounds, acoustic patterns, which are near and dear to my heart, as you all know. But today he's on the podcast really to follow up and maybe expand upon the work of his colleague and certainly his friend, Mordehai Milgrom, who was on the show this summer, joined us from Weizmann Institute in the land Eretz Israel in Israel. And we had a few audio connections. We'll still put a link to the podcast there. And Mordecai showed some of Stacy's slides. And so I thought it was due course to get Stacy on the podcast. Anyway, enough introduction. Stacy, how are you doing? How's my beloved Cleveland, Ohio?
I'm great. The weather here is perhaps not as charming as there, but it's not really winter yet. We had one decent snowfall, but now it's gone. So
okay. Yeah, we get snow here too. It's just like, in the mountains and very picturesque. But I really appreciate you joining. I know it's been a busy week for you, a lot of data and exciting opportunities for you. We're going to talk. Normally, we talk to authors. We ask them about their books and what inspired them to write books. I hope maybe someday you'll write a book. Maybe you'll kind of honor us by coming back on the podcast. But today we're going to talk about kind of a synoptic overview of this exciting turn of events that really, I have to say that you and Mordecai and a few other intrepid souls, Sabina Hassenfelder, my friend and colleagues, Stefan Alexander, perhaps Justin Curry, other people looking for alternatives or explanations that don't involve particulate dark matter. We've had on many, many people discussing dark matter and even discussing the only form of dark matter that I say we know for sure exists, which are neutrinos. Many people on. Elena April has been on. Kaishwan Ni has been on. So, Stacy, I want to ask you, you have a presentation. We're going to go through that and we had some audience questions. We're going to ask you those questions and it's going to be a lot of fun. So I really appreciate it. And just a reminder, you can always subscribe to the podcast here and leave questions for my guests here or on Twitter. I understand, Stacy, you're not on Twitter as much anymore. You're on Truth Social, as I understand it. So
I am trying to make the transformation to Mastodon.
If you figure it out, Govert Schilling was on the podcast this summer. He wrote a book called The Elephant in the Universe.
Yeah.
And so that would be the Mastodon in the universe. So if you figure out how to do it, I have not been able to apply my Case Western, Spartan or my Cleveland Guardian brain to make it work. But you are much smarter. You'll be able to figure it out.
Well, so it's like Twitter only in Linux. So you have to just take the plunge and then it'll come to you.
Get the servers running. Okay, great. So you have some keynote slides that you graciously agreed to present. And I think my audience will get a good kick out of it, especially since your audio is already about 10 to the 5th times better than good old Mordecai's was.
Oh, well, I'm glad to hear that because actually when we were teaching all through COVID, it was an off and on thing. So I'm glad it's on.
It is on. It's great.
Okay. Shall I share my slides?
Yeah, please do.
All righty. this is these are slides I've basically cribbed from the last time I gave a public talk to the physics club down in Akron. I've titled it The Acceleration Discrepancy because that was the term that Jacob Bekenstein used. And it's sort of really where the dark matter problem kicks in. But that goes a long way. So does that work okay for you? Sometimes it does.
Nope, that looks great.
Okay, good. So I like to start off with a philosophical quip that what gets us into trouble is not what we don't know. It's what we know for sure that just ain't show. So, and I've heard this attributed to Mark Twain, Lou Gehrig. I spent some time tracking it down, and near as I can tell, it's a paraphrase of Josh Billings, not quite what he said, but anyway, the things we know for sure are what Newton and Einstein taught us, and therefore the universe is full of non-baryonic cold dark matter. How did we get from A to Z there? There's a lot to it. And this is what I like to call the dark matter tree. It's sort of a sketch I made when I first had to confront this problem in a big way. So, I had a normal childhood like you. I was raised to believe in dark matter, and I understand all the reasons why that's a good idea, or at least a necessary idea. And so the sort of the empirical roots of the problem are there at the bottom, the sort of lines of astronomical evidence that lead us to believe in this stuff. And then the tree flowers into all these different ideas. And I scribbled this in, I think it was 1995. And I recently looked at a version done by some particle physicists, and it fits really well. Some of the names have changed, but they're really talking about the same thing, like strange nuggets are basically generalized to be macros these days and things like that. So very quickly, there are spiral galaxy rotation curves. They go faster than they should. There are all sorts of indications of discrepancies in clusters of galaxies. The gravitational lensing that you can see is rife in this case, but also the hydrostatic equilibrium, the amount of gravity you need to hold in the hot intracluster gas. And of course, the original velocity dispersion measurements going all the way back to Zwicky in the 30s. So all of these things point in the same direction, that you need more mass than meets the eye, or more generally, something extra, right? And so if we believe what Einstein and Newton taught us, then it has to be some form of invisible mass. But it's an assumption, a really good assumption, that what they taught us is right. But what if it's not? Mm-hmm. So, of course, from the cosmology side of view, one really important line of evidence is large-scale structure. You see this beautiful map of from the two-mass survey of where our galaxies are on the sky. So it's a whole sky map, sort of like looking at a map of the Earth, but looking up at the sky. Every dot is one giant galaxy, color-coded by its redshift, so how far away it is. And you can see these huge structures spanning across there, really large-scale structures. And of course, we started from a very smooth initial condition in the microwave background. And getting here from there is impossible unless you have some boost, like from some form of dark matter. Now, as an observer, I would like to prune the tree. I would like to cut off branches that are not promising, that are the wrong answers. And hopefully we could narrow it down to a single answer. And so very quickly, some of the early ideas were, well, maybe it's just some extra normal matter that we can't see. Brown dwarfs or lots and lots of Jupiters or something like that. And I'll just assert at this point, we can rule almost all those out. And that's been true for a long time. And, there are little corners of parameter space you can play with if you want to ignore Big Bang nucleosynthesis. But I have to say, I never took these seriously because Big Bang nucleosynthesis was already well established when I was young. And there just wasn't enough mass available in normal matter to make up the dark matter that we needed. So then there was the great idea of neutrinos. I remember hearing a talk by Andromeda in the 80s where he suggested neutrinos could have mass. And I was an undergraduate at the time who'd just been taught that neutrinos didn't have mass and that would screw everything up. And so I was like, well, that can't be But then I had the realization, well, maybe if it's true, that would surely be the answer. And of course, now we know it is true and it's not the answer. So there's mass and neutrinos, but it's just not enough to explain what we need. And so by a long way running, the most favored answer for a long time has been some form of cold dark matter, which usually is attributed to some new fundamental new particle. And for a long time, the most popular, and certainly one that was convincing to me, was the WIMP, the weakly interacting massive particle from supersymmetry. From the astronomical perspective, it doesn't have to be that, but it does have to have some important characteristics. And the motivation is one, as I already mentioned, Big Bang nucleosynthesis. This is the mass density in terms of the critical that you infer from all the different light elements. I won't go into that in any detail, but that is consistently less than what we get for the gravitating mass density. So there's stuff out there that seems to be gravitating that is not normal matter. So you need something new, like a WIMP. And the other thing, as we also already mentioned, is that you need to go from that very smooth initial condension of the microwave background, where these little fluctuations are only a part in 100,000, to these really huge structures where there's vast amounts of empty space, and then boom, a lot of structure. And gravity will do that for you. It'll make the rich get richer, and so the little fluctuations will get bigger over time. But it's also a weak force that takes a long time to do that. There just isn't enough time in the 14 billion years that the universe is to get here from there, unless you do something to goose the process. And that something can be some form of new particle, as long as it does not interact directly with the photons. And just through gravity. So that's the cold dark matter. And I was a big believer and proponent of that for many years, until I had reasons to doubt it. And one of the things that I find a lot of people struggle with is that it must be this way, because we're taught. And even I just got done teaching cosmology, and I taught that it must be this way, because that's what we do.
Right. I teach it. I had Barbara Ryden on. Sorry to interrupt. I had Barbara Ryden on the podcast last year, and she's written the book that's been read by more, undergraduates. I've taught from it for decades. She's an esteemed colleague. We don't really talk about Mond. There's a sentence about Mond, a sentence about alternatives. Yep. There's more on kind of the WIMP miracle. Maybe you could say something about the WIMP miracle. Are you going to mention that just as
I wasn't for time, but I certainly can.
Just in a couple sentences. What do people mean when when you hear the phrase the WIMP miracle?
So certainly one of the, maybe I do have something about that. There's the WIMPs. So the miracle was that we needed this extra stuff. And in fact, I used Barbara Ryden's cosmology textbook in the course I just taught. And so, we were convinced, I was convinced by this argument that, you need this extra stuff, and all the particles that you know about are in thermal equilibrium early on. And then at some point, as the universe expands and cools off, it freezes out. And if you ask what you need to what would happen if there were some particle that only interacted through the weak nuclear force and not through photons, well, then the relic abundance of that would be about right to be the dark matter. So these WIMPs, that was miraculous, right? There were just orders and orders of magnitude of what the right interaction scale would be to give you the right answer. And they were coincident with the one force that we knew about. And so it was a miracle, and I found that very convincing. Mm-hmm. Of course, since then, people have been working hard to find those particles and have not been successful. So the earliest, this is the sort of figure of merit that shows the interaction cross-section of these WIMPs, how they interact weakly with nuclei. And their mass, which initially was thought to be around 100 GeV, though that's really unknown, and people broaden their horizons as to what they're willing to consider for that. But that sort of upper region was the original prediction, and that was ruled out by 2008, which I call out because some colleagues here, this was before I'd even come to the case. I was at the University of Maryland at the time, but I participated in a conference here organized by Glenn Starkman and Tom Schutt and Dan Ackrum.
That reminds me, I did lie. I'm sorry. Glenn Starkman did a podcast before, so you're not the first case Western. So sorry, Stacy. We can end the interview now if you like. No, just kidding. Please continue. I forgot all about my good friend Glenn. Sorry.
Glenn's an obvious person to talk to, so that's good. So we had this meeting here, and you can see there was some moving of the goalposts. That the new prediction was that blue and green blob, and I'd become skeptical by then. So I was like, well, how much of the probability is in that head and how much in the tail, because you can see there's a long tail to lower cross section. And so far, up until that point, the history of the subject had been the experimentalists pushing down their limits more and more, and the theorists kind of moving the goalposts. And so I was afraid that would happen again. And at the time, the speaker assured me, oh no, 98% of the probability is up there in that head, and we'll find it pretty soon. Well, that's not what happened. And at this point, basically all of that area is excluded. So WIMPs were a great idea, as was supersymmetry, and there's just no evidence for them at this point. And so you can go a couple of ways and say, well, there are lots of other things the dark matter might be, and that's true. And it's also hard to make up good candidates that were as good as WIMPs. Or you can say, well, geez, maybe we were wrong to assume that we infer dark matter because we assume gravity works the same on all scales. Maybe that's not right.
Right.
And so that was really what came up in my own work. Galaxies are these important keystones in the whole problem. And the modern era of dark matter really took off in the late 70s, early 80s with Vera Rubin and Albert Bosma's observations of flat rotation curves. One can argue all the way back to the 30s from the work of John Oort and Fritz Zwicky, but nothing really happened with it until then. And now we've snowballed into this huge paradigm that involves cold dark matter. And there's a lot more to it now than what we understood at the time. We knew there was dark matter, so we knew there were flat rotation curves, so we inferred there was dark matter. So you take that galaxy, you observe it, and the actual rotation is flat, where the normal matter predicts that declining rotation curve.
And I can't.
And that's something that we see systematically in hundreds of galaxies now.
I can't.
And so.
Sorry. Yeah, I was just going to say, I can't resist, as is my speaker or my host prerogative, is to, let's see if I can get this to work. No, it won't work. Interesting. All right, let's see if that'll work. No. Anyway, I'm showing to the slides if you're watching on YouTube. This is a rotation curve. This is a galaxy image taken by Margaret Burbage.
Wow, that's great.
And the reason that's significant is that she then took a spectrum of the same object, which I'm showing here, these glass plates from the 1960s, when a scientist by the name of Vera Rubin was here at UC San Diego working with Margaret and Jeff Burbage, learning the techniques that Stacy was just showing. So I'm really thrilled to have a connection to these great titans of astronomy and cosmology. Although Jeff was not a fan not only of dark matter, but of all of modern cosmology, as you know. But Margaret was very sober and an exceptional astronomer of the highest caliber, right?
So, and I had cause to look up not too long ago that Burbage and Rubin collaborated a lot in the 60s to do this kind of work. And they didn't really detect, they detected something. They didn't quite get far enough out to see the flatness until the 70s. And I was just there looking through my slides because I often have some of those historic slides from Vera where, basically she'll have the spectrum that you showed, and then she had taken a picture of the reflection from the slit jaw. So you could see the galaxy and where the slit cut across it. And I don't have that in this presentation, unfortunately. But yeah, and so this has been known for a long time. And since we mentioned it, one of Vera's favorite stories was that when she first showed the flat rotation curve of Andromeda to Alan Sandage, he said, well, that's just the effect of looking at a really bright galaxy. And she was like, what does that mean? And it means that even really smart people say some pretty silly things when they're confronted with evidence that they don't get. And so Vera went out and observed 100 more galaxies, and they all did the same thing. And then, okay, that's what the universe does.
Yep.
And so this is what was known. So I would make the sociological comment that when the dark matter paradigm, as we now know it, really took off in the 80s, that was what was known. You had flat rotation curves. You need something to make up that excess. And early in that time, you didn't need a lot of extra mass. And so it was reasonable at first to think, okay, you have a lot of brown dwarfs or something. And then it kind of snowballed. Well, it's not just a factor of 2, it's a factor of 10. Now you're breaking the nucleosynthesis limits, and you have to invent some new kind of particles. And then there was this kind of shotgun marriage between the astrophysics of galaxies and cosmology with particle physicists who were like, oh yeah, we can provide those. And so, what we knew then was that rotation curves were flat and you needed something extra. And it snowballed from there. There's more to the story, and there's a lot of order to the data. And so this is a bunch of rotation curves of galaxies of different mass. And really big, massive galaxies rotate fast, and lower mass galaxies rotate slowly. And so those things I've labeled as gas-dominated, low surface brightness galaxies are the kind of things that I was working on. Mm-hmm. And it really surprised me the extent to which these followed the rules I'm going to describe. There was this thing called the Tully-Fisher relation, which was also discovered in the 70s, and it was used heavily as a distance indicator, as a sort of an empirical correlation between how bright a galaxy was and how fast it spun. Going over a lot of work. I've worked on this a lot. Every time I think I'm done with it, it drags me back in. But to make that long story short, the fundamental physical correlation seems to be between the mass of what you can see, both stars and gas, and that flat rotation curve, not any random measure, but specifically the flat part of the rotation curve. And so I call that the baryonic Tully-Fisher relation, because it depends on all the baryonic mass, the normal matter that we can actually see. And those little dinky LSB galaxies fall right on the same relation, which just surprised the heck out of me for a couple of reasons. One, they're more gas than stars. And if you correct for that, you add them together, then they're right on. So that actually makes sense. The part that doesn't make sense is that flat part of the rotation in the bright galaxies, it's got a contribution both from the dark matter and from the stars. You can't neglect the terms where we see it. These low surface brightness galaxies are basically like you yank away the stars, and so you would think they would have somewhat less velocity, all other things being equal. And that's not observed. And that's what really first made me concerned. I came up with all sorts of conventional models for why that might be true. And I found I was always engaging in some tautology, so assuming something to make it so. And it still confuses me to this day how we can explain this relation conventionally with dark matter. But just in an empirical sense, you can note that the galaxies all follow along the line of constant acceleration. And that's a theme that comes up again. If you want to make rotation curves flat, it's basically related to this scale. And so it comes up in terms of the Tully-Fisher relation. And then my contribution was focused on on low surface brightness galaxies. So just a quick description. High surface brightness galaxies are, there's a nice pretty picture of a spiral. Low surface brightness galaxies are the same, but the stars are more spread out, and so you barely notice them. And so I was attracted to that.
Is the Milky Way a high surface brightness galaxy?
Milky Way is pretty high surface brightness. That's right. And so the sort of low surface brightness galaxy that you're seeing there on the screen its central surface brightness near the middle is about the same as what we are at the solar circle way out from the center of the Milky Way. And so, you can zoom in and there's not much to see, but then you can take a high contrast image. And here I've turned up the gain so you can see the low surface brightness galaxy. And when you can do that, you see the diameter is comparable. The distance is comparable, which is like why I picked these pairs. It's about the same size, but the stars are much more spread out. And so this now is going to quantify why I thought there should be a shift of these galaxies off of the Tully-Fisher relation. That Newton told us that the velocity scales with the mass and the radius. These things, these low surface brightness galaxies, for a given mass of stars, have a bigger radius. They're more spread out. So you would think whatever the contribution that the stars make to V flat, and you can adjust that in your models, but they make some contribution. And so you'd expect some shift as you lower the surface density of the stars. And so each color here is a different bin of surface brightness going lower and lower. And as I went to lower and lower surface brightness, they did not shift as I predicted. So those lines are what I predicted. And so I was really annoyed. This was my prediction. It is a perfectly conventional dark matter-based prediction. And, I could have fudged anything, right? At this point, you say, okay, well, I was attributing too much to the stars, so the shift should be less. And then like I say, you start doing tautological things to make it work out. And basically, I could have explained anything but what I see. It just didn't make, because there's a fine tuning, right? You have to balance the dark matter contribution against the luminous dark contribution. As you're taking out spreading out the stars, you have to sort of backfill with dark matter. And so it's that fine tuning that really got me concerned with if it was right? This is a hard thing to know if there's invisible mass. How do you know to doubt it? And fine-tuning problems, pretty much the worst thing you can encounter. But it gets worse. So this is just one pair of galaxies plucked off of that plot, and they have the same flat velocity within the errors, and the same total baryonic mass. So you could not tell them apart on the Tully-Fisher diagram. But now you plot out their actual rotation curves, and you can see there's a big difference in the shape. And that's because there's a big difference in the concentration of stars. So one way to explain your way out of the lack of shift in Tully-Fisher, which is to say, okay, the stars weigh so little, it doesn't matter at all. It's just the dark matter. But if you do that, then you're basically predicting that the rotation curve shape should be just the dark matter everywhere. And that's not right. These things are the same mass, same V flat. They should have the same rotation curve, and they do not. And they do not in a way that clearly depends on how concentrated the stars are. The more concentrated the stars, the faster the rotation curve rises, and vice versa. This is sometimes referred to as diversity of rotation curves these days. And that diversity goes away if you consider the size of the disk. So here, this is actual length, kiloparsecs, meters, whatever length scale you want. Here you can fit some functional form to describe the disk, and they sort of really fall in line. And that's one of the systematics that has emerged since the systematic of the flat rotation curves was first discovered. Right. So whatever's going on, it somehow knows about the distribution of the starlight, not just the total mass, but how it's spread out. And so that's something that we have to explain no matter what. That's an empirical fact. It also seems to do with that acceleration scale I mentioned before. Here are the rotation curves of a whole bunch of galaxies from the SPARC project that Federico Lelli, who was a postdoc here, led. And the rotation curves have been color-coded by the surface brightness of the stars. And so you can see what I was saying, high surface brightness galaxies have high accelerations, low surface brightness galaxies have low accelerations. And so what you get does follow from what you see, just not in the way that Newton predicts. And so you can quantify that a bit more. This is what we call the central density relation. And there's a particular scale of surface density where this discrepancy sets in. So up above here, what you see really is what you get in the high surface brightness regime. Galaxies with bright bulges, pretty much the stars dominate the mass budget, and that's all you need. You wouldn't infer the need for dark matter. But you get further out, of course, rotation curves flatten out, and for these low surface brightness galaxies, you need dark matter or something, even at small radii. And so there is a break there. And this is what I say when it's predictive, that color coding basically is quantified by this. So the color is referring to that surface brightness. And so it's not just the center, as your perceptive audience members will have noticed. It's all along the rotation curve that this happens. And so the quantity, again, that really seems to matter is the acceleration. So on the top row, I've got a few galaxies with their rotation curves. The black points are what's observed. The blue lines are what you expect from what you see. And they're very different, right? You see a lot of diversity in the actual rotation curves. But then below that is a plot of the centripetal acceleration, v squared over r, that's observed there, against what's predicted from the observed baryons. So we see the mass in stars and the gas. We can solve Newton's equation, the Poisson equation, to predict what the acceleration should be. And if it were 1-to-1, it would just be that dashed line. And it's not, and that excess in velocity shows up as an excess in acceleration. But the remarkable thing is that these very different galaxies end up following very much the same line in this acceleration plane. So there's something important about accelerations. And so, in fact, you could put all the galaxies on the same plot and just bend them up, because you can't really tell the difference within the errors. And this is what we were hoping to check when Federico first made this plot. I happened to walk by his office and was like, Stacy, you have to see this. And I walked in and I was just amazed, because we expected there would be some outliers, because that's what always happens with astronomical data. But if you take just a little bit of care in excluding the data that you know are no good, there's nothing. They all fall on top of each other. So there's something really systematic going on. And it's worth remembering that dotted line there, that is what Newton predicts. So if there were no dark matter, no funny business, just what you saw was what you get, everything would fall on that line. Everything does fall on a relation. It's just not that line of Newton's. And so this acceleration scale keeps coming up in these different ways. The central density relation, the Tully-Fisher relation, this radial acceleration relation. This is a plot from Federico Lelli's recent review in Nature. So empirically, this acceleration scale is in the data. It's something we have to explain in any theory. And it's only at really low accelerations that this happens. So I've made this the ratio. This D now is the discrepancy, how much sort of effect you need, how much dark matter you need. And it's only at really low accelerations that this kicks up. You know, we understand things at much higher accelerations really well. We live here 11 orders of magnitude higher than the effect in galaxies. And you can go right the way up to emerging black holes. And, you know, our theory of gravity seems to work fine there. But you get down to galaxies and clusters, and you notice clusters are not quite on the same relation. But yeah, that's where the dark matter effect comes in. So that acceleration scale is critical. And so this brings us to Modi's theory. These systematic trends are present in the data regardless of theory. But Milgrom had hypothesized that, geez, maybe instead of invoking dark matter, we should change the force law. And so that sounds crazy, and it looks crazy. And many people tried this in a length scale, say, well, galaxies are much bigger than the solar system, so maybe something changes in between those scales. We can exclude that. That does not work. But what Milgrom suggested is that maybe it's not a length scale, maybe it's an acceleration scale. And he did that a long time ago in 1983. And so he knew then that rotation curves were flat. This was a way to make them flat. So that was the motivation, just like for dark matter. But then once you write down the force law, you're really stuck with it, and a lot of strong predictions follow. And so when I was struggling with this fine-tuning problem that I described, I happened to hear a talk from him, and I almost didn't go. I was like, modified gravity, who wants to hear that nonsense, And I went, and not knowing that I was in the audience, who I was or what I did, he basically, in a few lines, predicted everything that I was seeing that was confusing me. So I just wiped my jaw off the floor and went back and actually looked up his papers and actually read them. And I found this remarkable passage that disk galaxies with low surface brightness provide particularly strong tests. And, my bias in favor of dark matter was still so strong that when I read that, I was like, great, I now have the data that will falsify this stupid theory. I remember thinking that because I was just now pioneering the exploration of these low surface brightness galaxies more than a decade after he had written down these predictions. So a lot of these data, especially those for LSB galaxies, the low surface brightness things are working, simply were not available to inform his thinking when he made these predictions. Well, the first thing I realized is, and this is what he had derived on the board, basically, that blew me away, was that the Tully-Fisher relation should, have the slope that it was observed to have, a normalization that depended on this acceleration scale. He was the first one to suggest that it was fundamentally a relation between what you see and what you get. And it didn't matter if it was stars or a gas. It was the mass of all the normal matter. And the thing that really got me was that there should be no dependence on the surface brightness, that R in Newton's term drops out when you change the force law in this way. And that's what really got me, because I couldn't understand this effect at the time conventionally in terms of dark matter. And, that's just what's supposed to happen in this theory. He made other specific predictions that if you were to calculate the mass to light ratio in a conventional way, that would depend on radius. So these are the high surface brightness galaxies, and you can see the mass to light ratio going up as you go further out in radius. But as you go to lower surface brightness, you're going to lower acceleration in his theory. So the discrepancy should set in sooner and be stronger. And that's what we were seeing. All right. So the statement that low surface brightness galaxies are dark matter dominated, that came as a surprise to me. I didn't expect that. None of us expected that, except Milgrom. That was built into his theory.
Is there a, mechanistic way to see that in an acceleration, in a universe where there's dark matter, gas, or, ordinary matter? I mean, would you, would you first go towards a mechanism to modify the acceleration law? I mean, it seems almost counterintuitive that you get actual, honest to goodness, astrophysics, gastrophysics implications from changing, Newton's laws. But am I putting the cart before the horse, or is it a correlation, or is it, like the Tully-Fisher, we said, the implication is sort of it might just be, a correlation, but we don't understand the causation. But is this really distinct? Would you have gotten this if you just told Newton about this? Would he have predicted these properties?
No, he would not.
Right. I see. Okay.
And that's what I had been struggling with. You had to invoke various tautological effects in order to make it so. And that's commonly what's done today. Whenever you hear about people talking about feedback in galaxies, it's basically being invoked as a deus ex machina to make it so. But that's not what we predicted. The natural prediction for the lambda CDM universe that comes out of cosmological observations would be that dark matter halos have NFW-like halos, right? There's a specific functional form, and then you would add some baryons to that, and then that's what we should observe. And that's not what we observe. That's not equal to Mond, and basically Mond-like behavior is what we observe. And so to skip ahead a little, I would say that, basically the force law is unique, and the effective force law in galaxies looks like Mond. And so the thing that bugs me is that why should that happen in a dark matter universe? It's sort of like saying, oh, well, the solar system is really run by an inverse cube law. It just looks all the time like an inverse square law because the dark matter is arranged just so. Mm-hmm. That's incredibly fine-tuned. And that's basically what we have to end up doing to explain galaxy data with dark matter. You can do it if you're comfortable with that fine-tuning, go to town. But there is no more clear sign that we're on the wrong road in that fine-tuning, because once we've convinced ourselves that this invisible mass exists, it's practically impossible to falsify it. All right, how do we disabuse ourselves that we've gone down?
Right. Even not detecting it, is not grounds for eliminating it. Right.
You can also, and that's why I was sort of skeptical of the cross sections just ever moving the goalposts. It's like, well, you can move that down to zero, right? It's just
right, and eventually it'll be unfalsifiable because you'll end up in a regime where the supernova neutrino background will prevent you from ever making progress. And by the way, Stacy, the same thing could happen with me in looking for B mode polarization. It could be that inflation did take place, but at a very low energy scale, impossible for experimentalists ever to detect. And yet we can't rule out alternatives as well. Things like bouncing or cyclic models of Pascal Anna Aegis, Neil Turok, and Paul Steinhardt. That's maybe part 2 we'll do someday on sociology of when you can't falsify something. Do you rely on, social proof, on, going on Twitter or Mastodon? But lately things there've been a resurgence of interest in extremely low surface brightness objects.
Right.
Things like dragonfly. Can you talk about, are those challenges to Mond, as some have suggested in the audience, offline? What do you say about the dark matter, free galaxies and the dark matter only galaxy? And by the way, I don't mean any insult or anything. I'm just saying that's what they're called in the popular imagination. I'm not saying as
no, that's fine. So it's a lot, right? Every single galaxy is a test, and so you have to look at it on its own merits. And so when DF2 first came out, basically we did the Mond analysis, and the data, even though it was close to consistent with no dark matter, it was also consistent with the Mond prediction. At the opposite extreme, you have examples like Dragonfly 44, which had a much too high velocity dispersion. And I remember thinking when it first came out, I didn't even try. I just looked at it and said, well, that's wrong. If that's right, then Mond is wrong. Since that time, the measurement has come down to within consistency with Mond. And so I think the ultra diffuse galaxies, as we're calling these objects, are at the same stage that the low surface brightness galaxies I worked on in the 90s were at the same stage that what Burbidge and Rubin were doing in the 60s. Mm. And that as the data improve, I predict that they will revert to the mean that is defined by all the other galaxies, which also happens to look like Mond. And so I already have seen that happen for DF2 and DF44. Whether that will also happen for the other ones, I don't know. Right. And you have to take that as it goes. But I will say that I've been doing this for a long time now. And so I've spent an enormous amount of time over the last quarter century chasing up this example or that. And almost always, not always, because there are the clusters like the bullet cluster. I think that's a real problem for Mond. But this is a theory that people love to hate. And there are
what do you make of that? I mean, I don't like to always get into sociology. I've had on I've had on controversial thinkers and past guests, all different political and academic stripes. But what do you make of the ferocity and almost the dismissiveness that this can't be true because, A, we learned it in our textbooks, B, and often I should say, people like Barbara Ryden. She's not a militant, dark matter, adherent, but talk about the bullet cluster. I hear that all the time. Oh, it's almost like an excuse to stop thinking, right? And that's never a good sign in science, no matter what your stripes are. Right? So talk about the bullet cluster. To what extent, in a court of scientific law, whatever that means, is it useful? Is it dispositive? Because you strike me as somebody who certainly would be willing to be proven wrong. I mean, you've had many opportunities to be proven wrong. You've staked a lot on this. It seems to me that people like you and even people like Paul Steinhardt, who's got radical alternative views, would be more than happy to find out I was wrong. They don't think it's likely, and maybe you don't either. But talk about the bullet cluster, Stacy, if you would.
Well, so let me state first that I think one should state criteria that would make you change your mind, right? So I've done that, and I can restate those if you like. But to answer your question about the bullet cluster, I think it's a problem for all theories. And so it's one of the reasons I don't actually think there's a right answer that we know here yet. And it is a sign of the sociology that it is so often portrayed as a problem for Mond, which it is, but not also a problem for lambda CDM, which it is also.
Right. Now, I mean, the velocities in the bullet cluster are far higher than you'd expect. As I understand it, I'm not an expert. But that's a key critical lacuna in the particulate dark matter paradigm.
Yep.
Let me ask another question. So it is a challenge, but it's a challenge for both. But that's kind of, as they say on Twitter, whataboutism,
Sure.
So from the perspective, let me ask a more general question. If Mond, let's say God tells you, or, Gaia tells you, Mond is true. Could it be that Mond is only true on the scale of galaxies, but not on clusters and not on planets? Is that a possibility, or is that unlikely?
I sure hope not.
Right? No, we hope not. But
it's conceivable. And so there are people like Andromeda who are considering these neutrino hot dark matter, sterile neutrinos combined with Mond. And you mentioned Justin Coury, who has his superfluid dark matter model. And so they're sort of hybrid models that do the right thing dark matter wise on large scales and Mond-like behavior in galaxies. I will admit I have a philosophical distaste for such hybrid models. It feels like the Tychonic solution to the original scientific revolution. It's not, the sun's still at the center, but the Earth's still at the center, but all the planets go around the sun and the sun goes around us, and it's we don't know, right? I think we don't know. And I think the important thing is, as you said, is to keep an open mind and to be informed by all the data. And so, I tried this exercise of putting on different hats. And so, like I said, I just got done teaching cosmology. And if I put on my cosmology hat, I look at the microwave background and large scale structure and all the usual things. And I said, it must be that way. We must have cold dark matter.
Right.
And then if I put on my galaxy dynamics hat and I say, well, yeah, but we have an acceleration scale. We have baryonic Toy-Fitch relation. We have the radial acceleration relation. We have the ability to make the predictions for individual galaxies that we see. Then I say, well, then it must be Mond, right? Because Mond is the only theory that I've been able to use to make a priori predictions for what we're seeing. So just an example, and this relates back to your question about the ultra diffuse galaxies. So a decade ago, not quite, people were doing a survey around Andromeda, and they discovered all these new dwarf galaxies, very low surface brightness things. And I realized there was an opportunity to test Mond, because once they found them, they told me how luminous it was. I could use that information and Mond, and anything else really, to predict the velocity dispersions in these galaxies. And Mond was the one that worked, right? So there are a bunch of different observations. So the velocity dispersion for each Andromeda 1, 2, 3, is written out here. And then the Mond predictions came true in almost all those things. Those are the green circles. The one case that didn't come true is Andromeda 5. Mm-hmm. And so this is like the ultra diffuse things. There's one that's way off. But why did Mond work in all these other cases? That's really the question I've been asking for a long time that I haven't heard people answer, because they get a bullet cluster and they get the answer they want. Oh, look at Andromeda 5. The whole thing is wrong. And like you say, it shuts down discussion because, okay, I know it's wrong, so I don't have to even think about it. And It's hard to think in those different terms. So I get that. But a lot of these things were a priori predictions, right? I could look at the thing and I could say ahead of time what the velocity dispersion would be. And those predictions came true. That's what science is supposed to do, right? And so I guess my takeaway is that there has to be this phenomenology that we're calling Mond. It's telling us something. And Milgrom discovered something fundamental. He wrote down a force law that approximates some deeper truth. That deeper truth might be some grander theory of gravity. It might be something about the nature of dark matter. It does not come naturally out of cold dark matter. I've struggled for years to make that true, and I would really love to be able to say that's true, so I could stop having this kind of argument with everybody who I should be friends with, right? But it's and there are plenty of theorists who say, "Oh yeah, we can explain that in our models." Well, but you couldn't until I told you that's what the data said,
right?
And that's
violently react to you, right?
Yeah. So anyway, I mean, it's just an incredibly rich phenomenology that we are not really. It wasn't built into our models to begin with. All we knew was that we needed more mass.
Right.
Rotation curves are flat. We need something extra. That's not good enough, right? We need to explain why Mond happens in some very detailed ways, and maybe it doesn't in some cases, and that would tell us that Mond is wrong. But we still have to explain why it happens in all these other cases, and we don't right now. And just saying it's dark matter and some amount of astrophysics is the very picture of an unsatisfactory theory.
Right.
So.
Very good. Well, this has been a great treat, a great thrill.
It's fun to talk about.
Yeah, it's fun to talk about. Maybe if you want to stop the slideshow for one moment, I want to ask you. We have time for one existential question. I usually ask four, but in the interest of time in a late academic quarter semester, we'll only ask one. But before I do, there's been a lot of talk in the media, and actually, I have 2 or 3 videos I'll link over here, over there, with various folks and colleagues about claims that the Big Bang never happened because of the properties of medium surface brightness galaxies observed by JWST. And of course, this was also known or claimed to be known by a gentleman by the name of Eric Lerner, who's got his own YouTube channel, LPPF Fusion, I think it is, not too far from Cleveland. But anyway, he believes that the Big Bang never happened, and he has for some time since Hubble Deep Field, which maybe tells you something about maybe confirmation bias, I don't know. But anyway, he claims that the rotation curves and well-developed morphology of spiral galaxies at 400 million years post-Big Bang is a fatal flaw in the Big Bang. Now, obviously, well, first of all, I shouldn't, kind of comment before you comment. So I like your opinion. The problem with these people is that they always compare themselves to this guy, Galileo, the first observational astronomer, or worse yet, Stacy Giordano Bruno. Never compare yourself to Giordano Bruno. I don't care how good you are. But tell me, Stacey, what do you make of the new measurements that went originally Panic at the Discos or JWST? And we've had on people to discuss that. But what's your opinion? You're exceptionally qualified to comment on A, if the Big Bang never happened, or B, if JWST results have any bearing on lambda CDM, which I think would be very interesting to get your point of view on.
So first, I think the Big Bang happened. I haven't seen anything to make me question my fundamental faith in that.
Of course you do. You're paid by big cosmology, Stacy.
I am.
As Upton Sinclair said, it's impossible to get a man to think contrary of something that his job depends on him believing is so. Anyway, go on. I'm joking.
If I were following that, then it's cold dark matter. It's not just right. And so I do want to make that distinction that there's nothing in Mond that obviously contradicts that we live in an expanding universe in the broad outlines of the Big Bang, or even details like the early universe results like Big Bang nucleosynthesis. That's so early the universe is not in the low acceleration regime, so everything should be normal. Now, these JWST results are extremely interesting, and I don't think they contradict the Big Bang in any way. I do think they pose a problem for lambda CDM and its structure formation paradigm as we currently understand it. As you know very well, we have to go from that incredibly smooth initial condition indicated by the microwave background to a rich amount of structure now, and it's slow going. And what JWST seems to be seeing is that really big galaxies appeared quite early in the universe, within the first 500 million years or so. And that is much sooner than was anticipated in lambda CDM. So it's certainly a problem for our structure formation paradigm. I would make that distinction from the Big Bang in general. And I will say that Bob Sanders, using Mond, predicted that way back in 1998. He said, so basically you have to wait till decoupling around redshift 200. Up until that, structure formation in Mond is delayed because there's no dark matter to give it a head start. But once you get past that, the normal matter suddenly finds itself in a really low acceleration regime, and it acts as if there's just gobs of dark matter, and it forms galaxies very quickly. So he explicitly said that there would be L-star galaxies forming at redshift 10. And this was in 1998 that paper was published.
Yeah.
So I think there's a prospect of a real test here. Of course, we have to confirm what JWST is seeing. And that it's not just those where galaxies are big, but they're common enough to be a problem for lambda CDM. We have to make sure we've done the lambda CDM predictions right. And I think we have, but there are always knobs we can tune. But hopefully there's a real test there. And Mond did make a prediction, and it is consistent with that. So you don't have to throw out the whole Big Bang, but it may challenge the structure formation paradigm. And another quick point that your listeners might be interested in that regard is neutrino masses, right? The Planck satellite and the normal structure formation paradigm puts a pretty hard upper limit of 0.12 eV on the sum of neutrino masses. The minimum is 0.06 from the observed oscillations. Mm. And the problem with Mond is not making structure early. It's not overproducing structure by z equals 0. So it might help to have a little bit of neutrino mass. It might help things like the bullet cluster if neutrinos had a bigger mass. Yeah. The neutrino is only down to 0.8 eV. So that's another test. If the neutrino mass is somewhere in between, then that would be a really clear.
Well, with the Simons Observatory, we aim to get to the minimum mass level at about 3 sigma, and the minimum mass set level set by neutrino oscillation experiments, the minimum mass, as Stacy mentioned. So we'd get 3 sigma on that, which with cosmology. Now we'll have to have a follow-up on whether or not particle physicists will accept the measurement of an elementary particle, the last one whose mass we don't know, of all 17 of those little buggers. But in the remaining negative minute that we have, Stacy, I always ask existential questions, most of which are prompted by the namesake of the Arthur C. Clarke Center for Human Imagination that I am the associate director of at UC San Diego. We only have time for one, and that is a quote. He said many things. One is one of my favorites is for every expert, there's an equal and opposite expert. So you'd have to make a Mond version of that, modified Newtonian quip. But anyway, the one I want to ask you about is relevant to one of his laws, which is that when an elderly but distinguished scientist says something is possible, he or she is almost certainly right. But when they say something is impossible, and this podcast is called Into the Impossible, but they say something is impossible, they are most certainly wrong. I want to ask you, Stacy, what, if anything, would you say you've been wrong about, that you've changed your mind about in recent years? And it could be, inside or outside of science, but I'm curious for my listeners.
Well, certainly dark matter, right? I mean, I was a big believer in dark matter, and having Milgrom's predictions come true in my data really caused me that kind of existential questioning. And I remember spending nights awake staring at the ceiling. How could this come true? And, it did make me admit that maybe I had been wrong to believe so intensely that the answer had to be dark matter. Same thing happened with the bullet cluster when it was first announced, when the microwave background got out to the third peak. Those were both things that looked more natural in dark matter. So I was like, okay, maybe I was wrong to put so much credence in Milgrom having had his predictions come true. So right now I'm kind of despondent because it seems like everything is falsified. And we're not even really, as a community, I don't feel like we're really grappling with some of the most fundamental problems. I mean, even if Mond is wrong as a theory, all we're doing to explain it is, there's some gastrophysics and it sort of works out. And this is an answer that we would not accept in a junior lab project from our undergraduates, It's more fundamental than that.
That's right. Well, Professor Stacy McGaugh of the renowned institution known as Case Western Reserve University, my alma mater, my heart will always be with thee. I forget our theme song, but I'm sure it exists. I'm sure you could sing it along with those from MIT.
Go Browns, Stacey, right? I mean,
yes, go Guardians, right? Your new
exactly.
team. I actually got to see both of them play, and you should know one last bit of trivia for you, Stacy, is that because the Guardians, formerly known as a different name, because they won the World Series, that left San Diego as the only major city in the United States without a single sports championship in any sport that we've been involved with. And we came close this year with the Padres, but I always say, Stacy, the hardest job in the world is being a San Diego sportscaster, but the easiest job is being a meteorologist. Okay. I want to wish you a wonderful end of your semester. Happy holidays. I hope you come back on for a part 2 in the new year. And I wish you all the best. Thank you so much.
A lot of fun. Thank you.
Thank you. Bye, Stacy.
Bye-bye.